thank you for listening today. And there was already a question in the chat that was related to the examens. And as you might remember, we have two different parts of our exam. The first one is the written examen, and the day for the written examen is the 24th of February. And then we have the student conference, and that will take place afterwards at the 2nd of March. Yeah, so please have these dates in mind. And yeah, if you have no further questions or comments, then I would like to start directly with the lecture today. And what is our topic today is radiative heat transfer. So as you can see, we have only 3 lectures left this semester. And yeah, we went through all the topics of heat and mass transfer and different applications. And an important and interesting point that is left is radiative heat transfer. So usually, if we talk about transport processes, we have already always the transport coupled with mass transport, mass transfer, and fluid dynamics. And radiative heat transfer is an exception of that, because you don't need any, let's say, carrier for radiative heat transfer, as we will see. But despite this fact, in many engineering topics, radiative heat transfer is important. And therefore, I would like to give you some insights today and next week. Today, we will talk about some fundamentals. And next week, we will go a little bit more into details related to solar energy, because solar energy is probably the most important topic for the future, where radiative heat transfer plays a very important role. Okay, and yeah, the lectures are not very full, especially the lecture next week, so we will have some plenty enough time for questions and discussions as well next week. Yes. Excuse me?
On 27th, the last lecture that you have assigned, 27th. We have an exam on 27th.
Ah, yes, it's right. You have already examined. Yeah, yeah, you're right. I'm sorry for that. Yeah, we will switch the repertorium a little bit in front of that date. Yeah, I will tell you when we will do that. Probably on a Monday instead of the PBL. I will discuss this with class and with Felix. Okay, sorry for this. Yeah. Okay. There is already Sebastian Hofmann as well. Okay, so radiative heat transfer, as you can see here from our textbooks, many of the lectures, many stuff of this lecture comes from the textbook of Lienhardt. It's available online, and I very much recommend you to look into this book if you need some additional information and if you have some problems to understand what I tell you in the lecture. So today we need some special vocabulary that might be not so familiar to you, and therefore I would like to mention this special technical terms. So one is the emission. So emission, this is related to the, in German it's the same, it's the Emission, and it's a process of energy, how energy is released as photons. This is the emission in that case, so the release of photons. Another point is the emittance, and emittance in this case means in German das Emissionsvermögen, so this is the power of emission at the end. Then we have the point of incandescent, and incandescent means glühend. Maybe it's not such a familiar vocabulary for you. Yeah, this is glühend in Germany. It's an incandescent metal, for example. We have the topic incident, which means einfallend in German. So we have incident light. So the opposite of the emission is the incident light. And specular is probably known for you, means spiegelnd in German. So we have specular reflection as well. And another point is the intercepted. And intercepted means that we means auffangen, so aufgefangen. So we can have intercepted radiation. You will see this together with the lecture. It will make sense. Okay, so these are the points I would like to address today. Maybe I shift this here to the bottom, it's better visible. So we talk about radiative heat transfer. So after a brief introduction, I will give you an insight into bodies. We will talk about gray bodies afterwards. Then we go to diffuse and specular emittance. We will talk about reflection and the intensity of radiation, and the important Kirchhoff's law will be addressed as well. And here you see already some, I guess, well-known examples for where radiative heat transfer is important. So, for example, these days, if it's cold outside, then you know if you're close to a fireplace, then you will feel the heat, but this heat is not necessarily coming from some convective heat transfer, but it might come just from the radiation. So you have wind from behind, you will feel the heat in front of you because of this radiative heat transfer. And another very important example, of course, is the radiative heat transfer from sun. And this is for me the nicest, let's say, example why the radiative heat transfer has nothing to do with convection, because we don't have any convection in space, right? There is nothing that can bring us convective heat transfer, and therefore, of course, radiation is the only opportunity here to bring us some heat on Earth, which is extremely important for all the life on Earth, as you know. And yeah, the third example, here we have such a solar collector. It's a vacuum collector, and you can imagine inside of these vacuum collectors, vacuum means that we have no material inside for heat transfer by convection. We only have radiation, and this is also a good opportunity to reduce the losses, the heat loss of radiators, of solar collectors. Yeah, and this is why if you would like to design a modern and high efficient solar collector, you should have the radiation especially in mind, and you should optimize the radiation. So these are some points that we will address briefly, so that you should be able, after these two lectures, to design such a collector and to have a rough idea what is important and how this works. Good, so let's talk about this thermal radiation first. So fundamental mechanism of heat transfer, of course. Usually in process engineering, if you have any convection, then the convection will be more dominant than radiation. But there are, of course, some exceptions. For example, if you have no convection, or if you have very high temperatures, then radiation might be very important, and therefore it's good to know about that. Thermal radiation is actually an electromagnetic radiation. Yeah, thermal radiation belongs to electromagnetic radiations. We will see this in a minute. And it comes from the kinetic energy of the atoms or molecules. And they change their momentum by interatomic collisions. And this change in momentums that appears as soon as we have more than 0 Kelvin temperature. And at this moment, if you have a temperature that is higher than 0 Kelvin, then we have these collisions, and by these collisions, we have the emittance of radiation. We can't avoid that. Right? And this is the very, very small amount, but there's still an amount of radiation. So, and it's a charge acceleration, dipole acceleration that produces this electromagnetic radiation. You might have heard about the background radiation from space. It's a very, very weak signal, but we can collect this, and we can make some assumptions about how stars are built up from different materials, for example, and so on. Yeah, we can make some material analysis by the background radiation from space. We will see a little bit how this works in a few minutes. So yeah, you have a question.
What's the electron play a role in this? Like in case of like the electron from operation to ignition.
Yeah, laser. Yeah, laser light is using these kind of processes as well. Yes, yeah, you have the electrons that shift the orbit, and this also emits some radiation. Exactly, and that is, in that case, it's the laser radiation that is emitted. So the radiation can be on different wavelengths, of course, depending on the energy that is transmitted. We will see in a minute. So we have some examples here for thermal radiation. All of you know visible light, and of course, even visible light has some temperature effect about your these heating bulbs for growing up pigs, or if you have problems with your necks, then you can use these red light. It has a high energy and brings us also thermal radiation. We have infrared light that is emitted, for example, by an incandescent light bulb. We have infrared radiation that is emitted by animals. You all know these dark pictures from infrared cameras that just catch the infrared light. And yeah, cosmic microwave background radiation I already mentioned. So there are a lot of different important radiation effects. Yeah, and here you can see the full spectra of radiation. So this is a full electromagnetic spectrum, and it's necessary to have a look on that to understand the following slides. So this is, of course, somehow really related to the heat transfer, to heat radiation. So the radiation that we see is only this very tiny band here in this range between 3 to 400 nanometers. Here we have the ultraviolet light, and then the wavelength increases here from 3 nanometers to micrometers in the visible light region. Then we come to near infrared radiation and to far infrared radiation. So in these areas here we have strong thermal radiation, and you see the visible light is only a very small band here. It's only 0.4 to 0.7 micrometers in the wavelength where we have a visible light. So of course here we can directly see that heat is transferred. The other areas here are definitely not visible, and therefore we have invisible heat transfer radiation here in these areas. And now the question is, how can we calculate this intensity quantitatively, and how can we calculate how much heat is transferred by radiation from different wavelengths and light sources? And that's something I would like to address today in this lecture. And to understand this a little bit more in detail, first we have to talk about black bodies. So I don't know if anyone has heard about black bodies already. Do you know what a black body is? It's an important point here. So if we look to the spectra once again, and we know that the visible light is also transferring heat, then of course we should try to absorb all the heat that comes by radiation into our system. We should avoid that the heat is released from the system by any radiation. And in that case, heat is totally the radiation is totally transferred just into heat, which means into temperature. Yeah, so we need a system that catches all the radiation that comes from the outside, and let's say a trap of radiation. And if the whole radiation is trapped, then the radiation will be transformed to energy, to heat, so that you can measure the temperature, and then the temperature will be directly correlatable with the radiation, with the energy of the radiation. And this is the idea behind this black body, which means, you know, black means no light is emitted, of course, then it appears black. And so all the light it's trapped in this black body to be converted into heat. And this is how such a black body here might look like. There are different geometries and different systems, but this is the most simple one here. It's the so-called Hohlraum, and as you can see, Hohlraum is here the same expression in English. So we have this Hohlraum here, and if we have radiation of energy, so this is a ray of radiant energy here, and it enters into this Hohlraum, then it's reflected inside of the Hohlraum, and it's always reflected many, many times, as long as there's still some energy, and at the end, of course, all energy has been transferred to this metal outer body, and no radiation is left anymore. Yeah, so no light will be able to left this Hohlraum. And this is why all the radiation, all the light that enters the system is trapped here and is converted into temperature. And then you can measure the temperature, and you can check how the temperature, so the heat energy, comes from radiation, how the relation is between that. So in other words, we talk here about these three different opportunities. Body can absorb the incident light, so you have the absorbance alpha. So this is if a beam is here totally absorbed and nothing is reflected or transmitted. The second opportunity is that we have the reflectance, so the beam enters a surface, and then you know the optical law, the incident angle is the same as the exit angle, and so it's reflected. This is rho, the reflectance. And the third opportunity is that if we have a more or less transparent body, then of course a portion of this beam will also be transmitted through the body. Yeah? So this is here the transmitted ray. So these are the three opportunities. We have absorbance, we have reflectance, and we have transmittance. Nothing else is possible, and therefore the sum of all of these three different portions here is 1. And now it needs to be known that this depends also from the wavelength. So you know that for example, the transmittance depends from the wavelength. Think about your sunglasses, where you try to avoid to get too bright light into your eyes. So you have there a certain frequency and wavelength that is catched by your sunglasses to control the transmittance. Yeah, so and this is the simplest example, but of course, even for reflectance and absorbance, we have a dependency on the specific wavelength. Yeah, and now you understand from this point of view as well what black body means. Black body means we have only absorbance. There is no reflectance, and of course there is no transmittance. Yeah, so in other words, once again, all the beams that are hitting the body, the black body, are transferred to energy, to heat energy. So you can measure the heat energy, the temperature, and this is directly related to the radiation that hits your body. This is the idea behind that. And this can also nicely be visualized here from this example, and it shows that it's not totally trivial how heat is radiated. This is the so-called experiment of Leslie. So this is Leslie's cube. Here, this nice picture from Wikipedia, and you can see on the lower two pictures, this is a black and white picture, and on the upper hand we have an infrared picture that shows us with the infrared camera the heat. And what is visible here is that different surfaces cause different heat gradients. So this cube is filled with hot water, and the water temperature you can see is 52, about 52 and 54 degrees Celsius. And this means that if you would use a thermometer to measure the temperature of the surface, then the surface temperature will be the same everywhere on this Leslie's cube. Yeah, so all the different surfaces have the same temperature because you have a temperature, a fluid with a constant temperature inside. But if we look now with an infrared camera on this problem, then you see that the white and the black side, the painted sides, have a much higher temperature than the polished side. So the polished side on the right hand side is here is much cooler, and the reason is that, of course, here the radiation is strongly absorbed, so the radiation is stronger, and here we have also the opportunity of the surface to bring the heat by radiation, because you have this reflectance. Yeah, and you can also see that the heat that is emitted here by this hand, by the human hand here, even this heat is reflected in the mirror of the polished side of Leslie's cube, and you can see even the temperature of the hand here, because radiative heat can be reflected as well. Yeah, so this is a nice example that these emittance, absorbance, and reflectance have to be taken into account, and it's not totally trivial how heat is transferred by radiation. Yeah, this is the example of Leslie's cube. So the emissivity of the surface of a material is the effectiveness in emitting energy as thermal radiation, and this depends on the surface. So in other words, if you would like to enhance the heat loss, then you should not use polished surfaces. Yeah, because here much more heat is transferred over this black and white surface. By the way, you might be a little bit astonished that the black wall has the same temperature than the white wall. Do you have any explanation for that? Because usually if you would like to catch solar energy, then you paint a pipe or a collector black and not white. Maybe you would expect that the red and the black painted wall has a higher temperature than the white painted wall, but this is not the case. Any idea why? Yeah, it's quite a simple explanation here, because here we have mostly radiative heat transfer from the cube to the environment. Yeah, the higher temperature of the cube than the environmental temperature, and therefore it goes in this direction. If we would have a higher temperature at the outside, so if we use radiation to heat up the cube, then you would see that the black painted wall has a higher temperature than the white painted wall. But here we are talking about emissivity. So how is the heat transferred from the cube to the environment? Okay, but it has to be taken into account. So now, after we introduced the black body, we already know that it should be possible to find a correlation between the heat that is transferred, so the temperature of the body, and the radiation. And this indeed, this law was first found by two guys, by Stefan and Boltzmann, two German researchers, and they developed the very, very famous Stefan-Boltzmann law in 1979 and 1884. And so they found this relationship between the temperature and the emissive power. And they found this for the black body first. So they used this special opportunity to catch all the radiation in the black body, measured the temperature, and they found this very famous Stefan-Boltzmann law here that says that the emissive power for a black body, independency of the temperature, is these Stefan-Boltzmann's constant multiplied by the temperature to the power of 4. Very very simple and elegant equation. And this is the sigma indeed is a constant here. Oh, sorry. So you see that the flux of energy that is radiated from the body. So this is this emissive power. By the way, the unit is watt per square meter. And once again, this emissive power is depends on the temperature, but it's a wavelength specific power. So we have here the subscript lambda, which means that it depends on the wavelengths and as well on the temperature. But here for this simplification, if we talk about the black body, we sum up all the wavelengths because all the radiation is collected. Therefore, we don't have to distinguish here between different wavelengths. But if we look on the real spectra of emissions and radiation, then we of course have to think about a special emissive power here for one wavelength. And then we can integrate over all wavelengths to come to the total emissive power. But please have in mind the total emissive power is depending on the power that we have per each wavelength. So, but here we have the overall law for all wavelengths that is only valid if we have a black body, for sure, because otherwise, if we have reflectance, then you need to know which wavelength is reflected, and this means that you have another emissive power that brings energy to your system, to your body. So and here we have the equation from Stefan that enables us to calculate the Stefan-Boltzmann constant, and you see it depends here on the Boltzmann's constant, and it depends on the speed of light, and it depends on the Planck's constant. And because all these are constants, you see it's possible to use this as constant here on Earth. But of course, as already mentioned, if we talk about background radiation in space, and if we talk about material analysis of stars and all these crazy things from physics, then of course it's necessary to have this equation that can take into account different speeds of light and also different constants. Yeah, but on Earth, for you as engineer on Earth, I guess I don't expect that you will go to space with your engineering knowledge. I don't know, but hopefully it's not necessary due to climate change. Then probably you can use this law and just one constant 5.6704 multiplied by 10 to the power of -8. Okay, so this is a more engineering constant here. You can assume this really as constant. So now, if we think once again about these dependency of wavelength and energy and temperature, then you probably have already observed that we have another point, and that is that the wavelengths depends on temperature. And you know this from steel. You know, if we will have steel, for example, of a very high temperature, then it's glowing very bright and with a very bright color. And if it cools down, then the color gets darker and darker and darker. And the color is nothing else than the wavelength, what you see. And if the color goes darker, then it looks darker. It's more from bright yellow to dark red. Then it goes from a high to a lower wavelength. And this can be measured. And this shows that these wavelengths is directly proportional as well to the temperature. And this has been investigated by Wien, and here we have Wien's law, and these Wien's laws say that the product of the wavelength at the temperature is always a constant. This 2,898 micrometer per multiplied by Kelvin, and this is the maximum wavelength. And this means that if the temperature is increasing, then the wavelength needs to be decreasing. And that is what is shown here in this diagram. We have the wavelength here on the lower axis, and we have here on the y-axis the emissive power, the monochromatic emissive power. And as you can see, for high temperatures, here we have more than 1500 Kelvin. We have a very strong emissive power, of course. This is why we have here, why it's very bright. And you can also use the Stefan Boltzmann's law, yeah, that says that with increasing temperature, we have a higher emissive power. That is what you can see here from the absolute value, from the height of this peak. On the other hand, you see that the maximum of the peak is shifting. It shifts here from a lower wavelength to higher wavelength if the temperature goes down. So if the temperature goes down, then we come here to higher wavelengths because the product needs to be constant. And higher wavelengths, of course, means that we have different colors here. So we shifted from one color to another color, and now you have to take into account that we have the visible range of light only here, and therefore we come here from these lower wavelengths into this region here. Yeah, this is the only point we see. But in reality, we have a much higher, broader band of wavelengths here that are important for that. Okay, and yeah, here you can see this as well. So if we have yellow-white, then we have a temperature of the steel of more than 1300 degrees Celsius. And if it cooled down to 550, then we are at dark brown. Good. So this is another important aspect here. And then the next question is, how does the energy depend on wavelength and temperature? And this can be calculated with another important equation from another very famous German guy, and this was Max Planck. And Max Planck used this equation here from quantum mechanics to derive an equation for the emissive power for the black body. So take into account here these B for the black body and also specific wavelength. And whoops, Max Planck uses, this is not very surprising as well, the dependency on temperature, wavelength, and then we have here the Max Planck constant and the Boltzmann constant once again. So with this equation, we can directly calculate the emissive power of a certain specific wavelength. By the way, this might be also very important for, you have mentioned that already, laser applications. Because in laser applications, you always have a very specific wavelengths. Or think about new systems, for example, self-driving cars are using radiation, or think on your smartphone where you have these LiDAR sensors. Yeah, they sound so far away, and you will never need this knowledge, but it's all around us. Yeah, so it might be even for engineers important, or even just to discuss with the people who are developing these things, to know something about how you can estimate the power of a certain radiation, how this power is absorbed, how this power is transferred and transmitted. Okay, so this is the old and famous, but still very valuable and applicable equation from Max Planck. Yeah, and then I already mentioned it's important if you have radiation and the radiation hits a certain surface, how much of the energy is assembled from this surface and how much energy is reflected. And therefore, we need some laws and equations how the net heat flux looks like. Because it's something different than with convection. For convection, we have convective heat is just we heat up our materials, air or liquid or whatever, or fluid, and then the energy is convected. But in radiation, we have an interplay between two surfaces, because one surface radiates the heat to another surface, and there the heat is emitted, reflected, absorbed. And this, of course, affects also the emissive heat. So we have to think about the net heat flux in between. and this is something that we will address at the end of the lecture in more detail. But here we have a first slide for that. So you see here we have two surfaces with an infinite size, and these two surfaces have two temperatures, T1 and T2. And now we have here the heat that is transferred from 1 to 2, and this is area A multiplied by the emissive power for the black body multiplied by the temperature of the first body. But we have a second heat flux, and this comes from 2 to 1. And here we have also, here both surfaces have the same size, so A1 multiplied by the emissive power of the body, black body, and T2. And these two have to be taken into account, and if we bring this to a net heat flux, then at the end we have the difference. So first of all, we can make the difference here of both, so we have to subtract that. And then of course we know that the emissive power here can be simplified with Stefan Boltzmann's law to sigma multiplied by the temperature to the power of 4. So we can write the net heat flux as area multiplied by sigma, and then multiplied by the difference of the two temperatures to the power of 4. But anyway, it's a very simple equation. It's still a very, very simple equation to calculate radiative heat. Yeah. Yeah, here we have the emissive. Here we have the black body. It's a good question. Yes, if this is a black body, why do we have an influence of the second? That's your question, right? Yeah, it's a good question. Very good question. Why is it subtracted if we have a black body? That's a good question. I will try to find out and tell you next week, okay? It's an excellent question. Okay, however, this is a simple way. If we have two parallel plates on the same size, but you can imagine in reality you will also already have different sizes of the areas, and you will have very different and complicated shapes. So think about, for example, such a configuration here with a tennis ball-like surface, and here we have another obstacle. So how can you calculate the net heat flux in between these two particles? And it gets more complicated, right? Yeah, you have a question or comment? Yeah. Yeah. It's a black body, and the heat, and we calculate the heat Q just with the Max Planck equation and with the Stefan Boltzmann equation with the temperature of the body. So from this point of view, so here we have two bodies, but maybe that is, yeah. I'm sorry, I have to think about, yeah. I don't know right now, but if anybody else has an idea what's going on here, then please comment. Yeah. Yeah, of course, that's it. Yeah, you're right. You're right. That's it. The point is black body. Yeah, you're right. Black body is only related to visible light. Yeah, but of course, heat radiation is emitted from the body, even from the black body. Yeah, and this is related to the heat that is radiated from the black body to the other surface. Yeah, that's it. Yes. Thank you. Very good. I was a little bit confused with the light, but of course, yeah, it's we still can transfer heat, not in the visible light area. I already explained it, but I was confused. Okay, thank you. That's the right solution. Then the equation is correct. Okay. Good. So coming from this example to the next point. Yeah, here we have the net heat flux is the area and multiplied by Stefan Boltzmann's constant multiplied by the temperature to the power of 4. And in the case that we have not two parallel plates, then we have to take into account how much heat is here transferred and how the different areas interact. And therefore, we introduce this F factor, which is the so-called view factor. And I guess view factor is a very good expression for that, because it's related from what you see from one object. So if you are on this surface here, then it's related to what do you see from this object, because what you see from this object is also reachable by radiation from the other object. Therefore, it makes really sense to talk about a view factor, and we will go through some examples at the end of the lecture once again. Then you will get use of this view factor a little bit more in detail. Okay, so this is the black body, and now, of course, in your engineering test, you never will have to do with a black body problem. You will always have to do with emittance of containers, of pipes, of different obstacles. So how do you calculate the real emissive power of a non-black body? And therefore, we can use a very good simplification, because what we can do is we introduce a factor that gives us the deviation of the black body from the real body. And this simplification, this factor, is this fraction epsilon. Yeah, and the fraction epsilon is the so-called emittance. Yeah, we use the emittance epsilon, and this emittance gives us the factor from the real black body. So this means if we have these monochromatic emittance, then it's just for one same wavelength, and it's a portion of the emittance of this specific wavelength in ratio to the emittance of the black body. And if we want to come to the total emittance, then we have to integrate, of course, all of the different wavelengths here. We integrate over the wavelengths, and then we end up with our total emittance. And for black bodies, yeah, for sure, the emittance is 1 because we have no losses here in this case. And now the good point of the story is that, okay, we come to this in a minute. First of all, this means that if we have a non-black body, then we can use these emittance multiplied by the black body emissive power. And we know that this is can be calculated with Stefan Boltzmann's law. So the non-black body emissive power is here the emittance multiplied by sigma at the t to the power of 4. So of course we have the same problem because we don't know epsilon, right? So what is epsilon? It's just a trick to use a black body here. But there are two good points that I will tell you in a minute. First of all, we can combine now our two unknown points, the view factor and the emittance. So the view factor was how strongly do the two surfaces interact, and the emittance was the factor how strongly does the real system deviate from the black body, and we can combine these unknown variables in the so-called transfer factor. So the transfer factor is a view factor multiplied by the emittance. So we can calculate the net heat flux area multiplied by transfer factor multiplied by the Stefan Boltzmann constant multiplied by the difference between these two temperatures to the power of 4. Now this is the net heat flux between two bodies. View factor included and emittance included with the transfer factor. And of course, if one area is very, very small compared to the other one, then the transfer factor goes to the emittance. So now we come, first of here are some examples. So you can look up the emittance here for different temperatures, for different materials. Here, for example, we have polished steel with a very with the emittance here between 0.07 and 0.1. And if we look to another one, then we have here, for example, filaments. So these have a much higher emittance here of 0.39, because you can imagine it's not so strongly related to the black body here. In this case, if we have some filaments as, let's say, a trap of radiation in this case. So, and now the good point of the story, if we talk about the emittance as the factor that shows the dependency between black body and gray body, then we see that fortunately most of our practical applications have a very, very, let's say, wavelength independent dependency. So this is shown here from the sunlight spectra. So here we have the wavelength, and this is some monochromatic power. And this black line here is the real power, the real profile of the wavelengths of sunlight. You can see here the wavelength for different molecules. And the dashed line is the black body monochromatic emittive power. For the same for a body with the same temperature. So let's say if the sun would be a black body, yeah, and we can calculate the sun with this temperature for a black body, we can calculate the spectrum, and then it looks like this. And as you can see, it's a very valuable assumption to say that the real emissive power here of the black body is just we have just a portion of that for the gray body. So it's okay to say epsilon is constant for all the wavelengths. So we have one parameter here, epsilon lambda is epsilon, so it's quite epsilon is quite wavelength independent. Fortunately, this is a good point of the story in that case. This makes it not too complicated. So, and with that, we can say that the gray body emissive power is just epsilon multiplied by Stefan Boltzmann constant multiplied by the temperature to the power of 4. So what does it mean for the practical point of view? It's a quite simple equation. If you want to calculate the heat loss of a certain component of your process plant, and let's say the component has a temperature of 5,000 degrees Celsius, then you can calculate with the Stefan Boltzmann constant, the emissive power, and you not just have to look up epsilon from some tables from the textbooks, and then you can calculate how much power is transferred. Yeah, with this very, very simple equation, and therefore I guess it's worth to have a look on it that it's so simple. Yeah. Excuse me?
Can the temperature change? The temperature change is like I am varying at a particular temperature. I think here it is assumed the temperature means constant. Will it always remain constant, or can it change?
No, the temperature will be constant. So you can, of course, you can change the temperature here, and these emissivity, these emissivity will be constant. Yeah, this does not depend on the temperature in that case. Yeah. Okay, and yeah, let's give me the chance to give you another example from process engineering where this might be important. If you think about the applications of Professor Heinrich in solid process engineering, then you might know they very often do numerical simulations of particles that get dried in a fluidized bed. And these particles that are drying in a fluidized bed are sometimes quite hot. And so if you would like to make a very precise numerical simulation and you resolve each particle, then it's interesting to see how the heat transfer in between the particles runs. Yeah. And also if you think about a combustion chamber with droplets that are evaporating or particles that are formed that are agglomerated, then also the heat exchange in between the particles by radiation might be important. So there are some, not very much, but there are some applications where these radiative heat transfer can be important. Yes, you have a question. Good question. The question was for the people here they are online. The question was if there is a certain, let's say, critical temperature where radiation is so important that you have to take it into account. Yeah, it's a little bit difficult to answer because, of course, it depends on how strong the convective transfer is. If you have strong, and even in a fluidized bed that I've just mentioned, you have a strong convective transfer. So therefore, probably you can mostly neglect radiation. But if you are on a certain temperature level, but of course this depends on the convection, on the fluid, the dynamic conditions. It might get interesting. But at the end, I would say, as long as you are below 1,000 degrees Celsius or that something like that is a rule of thumb, there is probably not no necessity to take into account radiation. And no, of course, convection is always a very important fact. And mostly, the heat transfer by convection will be higher than by radiation. Yeah, I think so. Yeah, another point, of course, it depends also on the distance between the particles. Yeah, because the closer the distance, the higher the pressure drop, the lower the velocities probably, and therefore convection might be less important than radiation. So it's not so easy to answer this question. It depends. Yeah. So I guess you can put this very behind your mind into the last cell of your brain, but maybe that sometimes you should think about maybe radiation plays a role. I had this one or two times in my professional career that I remember radiation, and that was indeed an important point because we had some more heat loss by a factor of 1 or 2 by radiation, which is a lot. But for most applications, engineering applications, not so important. Yeah, but with this equation, it's not difficult to make a rough estimation if it's important or not, right? We have some other examples. Think about diffusion. It's the same question. When is diffusion important? If you look for a convective flow, that's a question that we always address. So usually diffusion can be neglected as soon as you have convection because it's such a small amount of transfer of mass and heat. But yeah, in special cases, this might be important. And another example is, just had that in mind, now it's gone. Diffusion. Oh, sorry, I don't remember. I remember later on. But sometimes there are exactly these questions. Is it relevant or can you neglect it? And mostly it can be neglected. but nevertheless, it's good to know about this phenomena. Okay, so talking about these reflectance, so we strongly talked about the emittance already, together with these black body and gray body assumptions. But what's about the reflectance? And therefore, we have to distinguish different surfaces with different reflectance efficiency. So the energy is emitted by a non-black surface, leave the body diffusively or specularly, we say. And a mirror, for example, reflects visible radiation perfectly specular. And if you have diffusive reflection, then it looks like this. So here we have the specular reflection. Yeah, the income angle is the same than the outgo angle here. So this is the total reflectance. And here we have a total reflectance, but with a diffusive reflectance, yeah, where the reflected light goes in different directions. So this is probably like a mirror here, and here we have a more rough surface probably. And if we have a rough black surface, very homogeneous, then we might have this total reflectance only in a diffusive matter here. Yeah? So here we have only diffusive reflectance. This has to be taken into account if we want to calculate the radiative heat transfer. Yeah, you can imagine this might be important for solar collectors, right? Because if you have your collector where the heat from radiation is collected and transferred into the body heat, like water, if you want to heat up water, then you will try to totally avoid this reflectance. Yeah, or at least you will have a diffusive reflectance, and the shield around these tubes, these heating tube, there probably you will try to get a total reflectance, and this is a diffusive reflectance as well in that case. Yeah, because then most of the radiation that is reflected can be collected by the heat pipe anyway. And so next week we will talk about more on this topic, how to design the surface in the right way. So if we have this diffusive reflectance, then unfortunately it gets more complicated to calculate how much radiation is collected, because the diffusive radiation goes in such a hemisphere direction here. So we have a half sphere here, and if this is a spot of radiation and we have diffusive radiation, then the radiation will penetrate here into space in these hemispheres. So you have to calculate the amount of heat that is here collected, and this is a equation for that. Here we have the heat flux. This is cosinus phi multiplied by dA. So dA is the surface here. This is area where the reflection comes from, and phi is this angle here, and then we have additionally the angle C here. So we have to look on this tiny piece of the hemisphere, and we have to multiply this by the omega, so the angle, and this brings us the net heat flux. And here you see these I, and I is a special parameter. It's calculated from the black body emittance divided by P, and the unit of this I, because we have here the pi taken into account, the unit is watt per square meter, and steradian. Looks a little bit strange, steradian. So what is steradian for a kind of unit? And steradian, and I picked up this here from Wikipedia to bring this into your mind again. I didn't know that before, I have to say. I have to look it up by myself. So if you have a circle, and then you have the radian. This is here the radian, and the radian brings you the length of a part of this circle. And the steradian is the same, only in 3D. So what brings you here, this line of the circle brings you an area of the sphere. It's a part of the area. Yeah, and as this line here depends on the angle, we have another, the area depends here on this steradian angle. Yeah, so this is a steradian. It's a surface because we are in 3D. And this is why we have here as per steradian. It's not per grade, yeah, like it would be in 2D. In 3D, it's watt per square meter and steradian. So with this equation, we can now calculate the outgoing heat flux for such a situation. Good. So one important law is missing. We talked already about the law that brings us the heat flux, the radiative heat flux in dependency of the temperature. This was a Stefan Boltzmann equation. We already talked about Wien's law that brings together the wavelength and the temperature. And now we have here Kirchhoff's law. And Kirchhoff's law tells us how these monochromatic absorbance here depends on how this is related to each other. The emittance, the monochromatic emittance for one wavelength, and the monochromatic absorbance. And Kirchhoff's laws say that the radiative absorbance for a certain wavelength is the same than the radiative emittance for a certain wavelength, depending on temperature and these two angles. We have these diffusive emittance. And this means for a diffusive body, we have to take care about specific wavelengths. For a gray body, as you know, for a gray body, we assume that the emittance is constant over all wavelengths. We can assume that this is really the same. So epsilon is the same than alpha. So this means if a body has a certain absorbance capacity, then the emittance capacity will be the same. Yeah, this is a simplification by Kirchhoff's law here. Yeah, your question is, will it always be in equilibrium, these emittance and the absorbance? If you have a gray body, yes.
But can the body temperature change?
If the body temperature change, yeah, the temperature of the body can change, and then the absorbance will change, but the emittance will change in the same way.
But they will not be the same. The body temperature.
They will not be the same. It depends on the temperature. Yeah, that's what these brackets and the dependency of T's here means. Yeah, emittance and absorbance depends on the temperature, but with Kirchhoff's law, we can assume that it will be in the same order.
It will be the same, but the value will be new.
Yeah. Yes, it will be the same, but the value will be new. Yes.
Oh, if a part of the mission is to increase the temperature of the body, you are heating something with radiation.
Yeah.
So some part of the energy should be lost as to increase the temperature. If emittance is equal to absorbance is equal to emittance, there is a part of energy that is coming. If I am just using the laser or something to heat something.
I don't understand. Yeah, what you might have in that case is different. The transmission, for example, is not taken into account here. Yeah, so epsilon plus alpha plus tau, the transmission is 1, and so the transmission might vary in that case. Yeah. Okay. So this is the most important point of Kirchhoff's law. And now we have all together to apply this. So here, for example, we can calculate once again. We have our two infinite plates, one minus infinity to plus infinity, and this is on temperature T1. This is on temperature T2, and we would like to calculate the net heat flux once again. We know that we have to use the emittive power first. So we use the emittance here for the certain wavelengths dependent on the temperature multiplied by our emissivity of at the certain temperature for these certain wavelengths. This is what is emitted by plate 1. Yeah. And then we have the radiation from plate 2 absorbed at plate 1. And this has been subtracted as before. And here we have the absorbent independently of the temperature, and once again emissive power of the black body of T2 multiplied by d lambda for each flank. We integrate this over each wavelength, and if we combine this, then we end up with this equation here. So epsilon multiplied dependency of the temperature multiplied by Stefan Boltzmann constant, temperature to the power of 4, and minus absorbed. So the emitted light minus the absorbed light from plate 2, for sure. This is what we have as net heat flux. Yeah. Good. So, if we use now these gray body approximation, then we can have this example here. We have plate 1 is painted with white paint, and plate 2 is at the temperature near plate 1. So let's say both temperature, so temperature 1 is 400 Kelvin, temperature 2 is 300, and we have approximating that both is on the same order, epsilon and alpha, and then we have as net heat flux epsilon multiplied by sigma and the temperature difference here. So plate 1 is approximately this gray body once again. So, and now at the end we come to this U factor, and yeah, we already talked about the view factor. That is how the name says. It's what does you see, what kind of radiation do one surface see if you look to the other surface. And give me 1 minute, I have to sit down because I have a little bit problem with my blood circuit. Just a few minutes, I don't know what's going on, maybe
do you need water?
Yeah, that would be nice. Can you have some water? Maybe I have not drunk enough. Yeah, that's a good idea. Yeah, maybe.
So much. Take it also.
Wow. Yeah, we have both windows are closed, right? Thank you so much. It's fine. I feel good, don't worry. It was just a little like this, and so it's better to sit down before I fall down. I know I'm not used anymore to stand here for 1.5 hours because quickly I'm sitting on my my desk chair. Probably this is a problem. So thank you so much for your patience. I guess I will be able to finish now. We have not so much slides left. Yeah, the view factor. So this is a nice example that helps you to understand how this view factor works. Here we have three different opportunities. One is that we have the two parallel plates. We already have talked about that. And here we have a sphere above plate. I'll think about Professor Heinrich's fluidized bed. This might be a particle. And here we have maybe a very hot surface. The question is, how does heat transfer by radiation happens in between the particle and the wall? And here we have a wall that is in 90-degree angle to another wall. And this one is a very short wall, wall 1, and wall 2 is of infinite size. And now the question is, how can we calculate the net heat flux in between? And the easiest way is to think about that the view factor F12, if you read this as fraction of field of view of 1 occupied by 2. Yeah, so the easiest way is to think about the first digit here is the surface you're located at. So here we are at 1. And we're looking to the second object here to 2. Yeah, and when the surfaces are each either thermal and diffuse, then we can say that F21 is a fraction of energy that leaves 1 and reaches 2. Yeah, but I recommend to use the first one first. So this means, here we have the example. So here, of course, both view factors are 1. Yeah, because from this point we see that and vice versa. And in this case, if we have the view factor 1 to 2, and we are sitting on 1, and we're looking in this direction, then at half of the area here, we will see the surface, and on the other half of this particle, we will not see any surface. This means here we end up with 1/2. And 2/1 means if we are located on this area and we look to the other one, then we only see at a very small amount in our view field here, the particle 1. And this is so infinite small that we can say this goes to 0. Yeah. Sorry, I have to sit down once again. Bitte? Also kann ich auch mitmachen. Ja. I guess I get old. Okay, so yeah, and usually if we have a more complex situation like here, where we have this very complicated shape and another complicated shape, then of course we have to split this into different sections, and then we can calculate this with the view factor 1,1, 1,2, 1,3, and so on. Yeah, so here the view factors are separated into single parts. Okay, and now it gets, of course, a little bit more complicated if we have these different orientations, but I guess it's not necessary to go here now into more detail. It's just a little bit arithmetic that has to be taken into account. Okay, and easier is to look at just up in tables. Here we have tables that explaining the different view factors for different configurations for example, in solar panels, you might have a situation of these parallel pipes here, and then you get view factors from tables that can be calculated, sometimes with a little bit more complicated equations here. But anyway, it's not very difficult. It's not any rocket science. You can do this with the simple equations. It's just necessary to know that it's not as simple as with convective heat transfer, where you have the heat transfer just in one direction. For radiation, you have always taken into account the second surface that is in the vicinity of the first one. Yeah, and of course, one more comment. On Earth, in reality, we have, of course, several disturbances of the radiation, so that the distance, at a certain distance, there is no effect of the second body. But if you think about radiation in space, now there we have vacuum, so there is no other influence, no resistance and no influence, and therefore much higher distances have to be taken into account if you would like to calculate these view factors, especially, for example, if you would like to calculate how sunlight hits the Earth. That is something we will address next week. Okay, and yeah, some other opportunities. Here we have two circular systems, and with this two circular systems, we will have a calculation next week. At the beginning of next week's lecture, we will have an example calculation for radiative heat transfer for a heat radiator. And you will see how to use the equations we talked about today, and also how to use these view factors here. Okay, so that's all for today. Do you have any questions left? I know it's a lot of complicated stuff and not very easy to understand, but I hope that you got a first impression what radiative heat transfer means, and how you can calculate, or let's say just rough estimate if it's important or not. And this is, of course, Stefan Boltzmann's law. If you know the temperature, the constant is given, you can calculate how much heat is transferred, and then you can compare this with the heat that is transferred by convection. As mentioned before, you can neglect it. Okay. Good. If you have no further questions, then let's go next week to this example of radiative heat transfer, and we'll talk about solar energy. And yeah, the repetitorium, I will tell you via StubIP how we will treat that last lecture. Yeah. Okay. Good. Thank you very much for listening, and then enjoy your afternoon. There's one point in the chat. So, yeah. Okay, Brenk. Okay, you have an. Would you like to give us your comment? Is it related to the lecture or independent of the lecture? I don't hear you right now.
It's related to the lecture yesterday, but I don't know if it's for everyone.
Okay, then we can discuss this just we two maybe, and if it's important, then I will address this next week.
Yeah.
Lecture. Yeah. Okay, perfect. Ja, but please go ahead.
Ja, dann können wir es über die Woche. Gestern ging es ja auch noch mal zum Ende der Vorlesung um Druckverluste in Rohrkrümmern für Zweiphasenreaktoren.
Genau.
Und ich war sowieso gerade dabei, ich schreibe den Abschnitt, also ich bin ja aus einer der Gruppen, die diesen Reaktor haben, diesen Reaktortyp. Und witzigerweise habe ich gerade den Abschnitt geschrieben über Druckverluste.
Ja.
Und hatte gedacht, ich gucke einfach mal nach und habe einfach mal ein bisschen rumgeguckt, ob ich was finde zu Druckverlust oder zu Druckverlusten für Zweiphasenströmungen in Rohrkörpern. Und also ich war da jetzt nur recht grob unterwegs gestern Abend, aber ich würde sagen, da gibt es doch aktuell einiges, was da wieder an neuen Erkenntnissen hochgekommen ist. Und es sah wirklich danach aus, als wenn man das nicht direkt einfach vernachlässigen kann, übergehen kann, so wie der Brauer das gesagt
super.
hat. Also ich habe jetzt keine detaillierte Recherche da betrieben, sondern einfach nur mal ein bisschen quer gelesen.
Ja.
Und also es gab Gruppen, die da versucht haben, mit korrigierten Martinelli-Korrelationen irgendwie was zu machen oder so. Also ich glaube schon, dass es da eine Vielzahl an Forschungsprojekten auf jeden Fall zu gab.
Ja, super, das würde mich sehr interessieren. Vielleicht können wir es so machen, also Sie sollten das in jedem Fall dann mit in die BWL aufnehmen und auch kurz darstellen, ja, dass Sie da was gefunden haben und was Sie da gefunden haben, das wäre schon toll. Und ja, ich selber bin natürlich auch sehr daran interessiert. Also wenn Sie da was rausgesucht haben, fände ich sehr nett, wenn Sie mir das vielleicht einfach zuschicken würden. Okay. Das in Zukunft mit berücksichtigen.
Achso, ja, okay. Also dann schaue ich nochmal, wenn ich da wirklich was Brauchbares finde, dann würde ich das weiterleiten.
Das wäre super. Prima.
Alles klar.
Okay, alles klar. Vielen Dank.
Jo, ciao. Tschüss.